Hey everyone, we're going to go through our second lesson for this one. For this, we're going to look at amplitude, wavelength, and phase, which are kind of like the three different ways that we measure like a wave, like how long it is, how tall it is, and where you are on the wave. So as long as you know what those are, you're good. There's also a quest assignment that goes with this, I think. Yes, so make sure that you do that after you watch this video. Okay, so let's say we have a wave, right? We talked a little bit about them last time, and you can have a couple different waves. So I'm just going to draw like a pair of different looking waves here. We get a wave that looks like this. Oh, where'd you go? Oh, a wave that looks like this. I don't know. I'm just going to draw another one. I don't know, and then a wave that looks like this. Okay. Clearly, there's some differences between these two waves, right? One looks like, I would say that this one looks taller than the other one. This one's more like, it's like shorter, but like more stretched out. But in physics, right, we don't just talk about like, oh, like this is bigger than that. We put numbers to this. We can like measure them and assign a value to those quantities, like the height and how long it is. And actually, those two values, we call them amplitude and wavelength. So let's get a couple quick definitions here. So for an amplitude, our definition for amplitude will be, it's, how tall the wave is. That's basically what it means. It is measured from what we call the equilibrium line. I'll explain what that is in just a second. So it's how tall oh my god, sorry. It's how tall the wave is measured from that equilibrium line. The amplitude is related to the amount of energy that the wave has. So it's related to energy. So when I say it's related to energy, if you kind of think about it, it makes a little bit of sense. Like imagine a water wave with a lot of energy. You're probably picturing like a really big wave, like something very tall. And that's because that high amplitude, or all of that height, there's just a lot of energy associated with that. The equations and such that actually, to calculate the energy related to a wave is actually sort of a very complicated sort of thing. So we're not going to do that. But if you understand that a lot of amplitude means a lot of energy, that's good enough for us. So, when I say measured from that equilibrium position, I'm going to draw a wave, but before I do that, I'm going to give us like a reference point here. So let's go with like a thin, dark line. So this is going to be like flat. So imagine like a pond or a puddle. This is just like it's undisturbed, it's perfectly flat. And if we sent a wave through it, it would make like some parts go high and some parts go low. We call those the crests, the high parts, and the troughs, the low parts. So I'm going to draw that in here. Let's change colors. So let's start here, and we go up, we go down, we're back to where we started, we go up, we go down, we're back to where we started. And that's good enough for us. So what I drew is two complete waves. Two full wave cycles. A wave cycle is you take where you started. Can I do highlighter mode here? There we go. Take where you started. Didn't do what I thought it would do. From where you started. No, it's not doing what I thought it would at all. So you go from where you started. You go all the way up, all the way down, and then back to where you started. That is one complete wave. Or you can go from all the way at the top to the bottom and then back to the top. That's also one complete wave. Because you see how you went from like where you began to the next time that occurred. Getting back to amplitude. Amplitude is a measurement, again, of basically the height of that wave. So, for this one, the amplitude is this. I'm going to give it an A for amplitude. So that measurement would be an amplitude. We would typically measure it in meters, maybe centimeters, because a lot of times waves can be very small. Like, imagine small ripples in a pond. You probably wouldn't measure those in meters. An important thing about waves is the height of the wave should be equal to the depth of the wave. And again, we have words for these, so I'm gonna just write in that wording. I don't think I brought it. I don't think you have it in your notes yet. We call it a crest and a trough. TRUGH. So that amplitude is essentially the height of the top of the wave, and it's also like the depth of the bottom of the wave. They should have the same value for a wave. If you're in any kind of pre-calc, I think maybe trig, I'm not sure what math they do all of this in, but if you've done sine waves or cosine waves, this is just that. It's the amplitude is how high up it goes and how far down it goes. It's not any different from that. We're actually keeping it even sort of simpler than that. So that's what amplitude is. How high up, how far down, and then it is related to the energy of the wave. Lots of amplitude, lots of energy. Wavelength. Oh man. The definition is what it sounds like. It is the length of a wave. I don't want to write that. I'm going to write the length of one complete cycle. Just, that way it's a better definition than the length of a wave. But that's basically what it is. We use a Greek symbol for this in equations. We're not going to do the equations today, but it is nice to have a shorthand here. We use the Greek symbol lambda, which is like a squiggly sort of thing like that, and there you go. That's the Greek symbol lambda. Let me pull up a typed one so you can see what I'm trying to draw. So that... I'm so sorry. That Greek symbol lambda, that's this guy right here, and that's what I'm trying to draw. We got that little like kind of squiggle thing, and then this little diagonal right there. So I'm going to draw that for our wavelength. I'm going to label a couple wavelengths here. And again, it's just how long a wave is from where it starts to where it ends. So our wave, it starts here. I'm going to trace a full wave. When I'm doing it, I typically trace with my finger. I'll do it with my mouse pad now. And I've been teaching this for years and years. And when I'm counting waves, I literally have to follow with my finger. It just helps. It's easy. So we start there. We go all the way up, all the way down, and back to where we started. So it looks like that wave ends here. This length right here is one wavelength. I'm going to label it with a lambda. Ugh, that turned out bad. That's okay. I'm going to label that lambda. Now, if we don't start at the bottom, like let's say we started at the top, I'm going to go one complete wavelength from here up to here. Notice we start at the top, we end at the top. This is also one complete wavelength, lambda. Let's change colors because this is going to turn into a line of the same thing. Or I could start at the bottom and go, okay, all the way up. Oops, sorry. All the way up, all the way down, and back to that point. This would be one wavelength. Or, just to bring the point home here, we could start, let's start here actually. Okay, here is like where we're going like down on the wave, right, as we go this way. So, we go from here. We still have to keep going because I know that we went from like that 0 point to the 0 point. But see how this is like where we're going down and this is where we're going up. So here we go all the way down, all the way up, and then back to here would be one complete wave. So this is also a wavelength. If I was any type of good at drawing, which I'm very much not, all of these lengths would be exactly the same. Like if you could move them and place them on top of each other, they would be exactly the same length. And we call that a wavelength. Since it's a length, we're going to measure it in... I hope you were like thinking the rest of that sentence. Meters. Again, it's a length. It's how long it is. All right. Let's go. Try a couple of problems with this. Drawing waves. because it's good to get some practice with that. For number 12, the diagram below shows a wave. On the diagram, draw a second wave with the same wavelength but smaller amplitude. Do me a favor here, pause the video. Think of what this should look like. Take a guess. Do that for me. Pause the video. Give this one your best shot. I'm going to go over it though. Okay, hopefully you paused it and gave this one a chance. The diagram shows a wave. We're going to draw, the same wavelength. Remember, wavelength is, I don't want to sound stupid here, but it's how long the wave is, how stretched out it is. So if I look at a wave here, we've got, alright, we started here, and then a full wave. I'll trace it with my mouse here. So all the way up, all the way down, and back to where we ended. So our full wave should complete that cycle by the time we hit here. Okay, good. But we need a smaller amplitude, which means that we're not going to go quite as high, we're not going to go quite as low. So, but again, I want that spacing or that length to be the same. So I'm actually going to even try and hit the 0 mark right here. So, alright, so we go up, and then we go down, and then back to where we started. Well, there we go. That's an okay looking wave, right? And that works. Again, the reason the wavelength here is the same is we start here, and we end here, which is, oh god, that turned out bad. And we ended here. That's the length of one wave. So they both have the same starting and ending point. So they're both, one's just as long as the other. But one has a lower amplitude, meaning it doesn't go quite as high, doesn't go quite as low. So it has a little less energy, which causes it to not, again, have the quite as large of a fluctuation there. Great. 13. Actually, for each of these, as I get up to them, pause the video, try it on your own, and I'll go over it. So take this moment, pause it, and take a guess here. I'm hoping you took that awkward pause to stop the video and give this a shot. Alright, the diagram represents a periodic wave moving along a rope. On the grid, draw at least one full wave with the same amplitude. So same amplitude means we go just as high and just as low as the other one. But we're going to do it in half the wavelength. Okay, so let's do this. Let's figure out what the amplitude is, and we'll figure out the wavelength is, and we'll work from there. So the amplitude should be the same, right? So amplitude is... The amplitude of this is, looks like it goes up to 0.1 and down to negative 0.1. So the amplitude is 0.1 meters. Meters, because I'm getting that from that y-axis. So we're going to draw something with the same amplitude. Let's look at the wavelength. What do you think the wavelength is of the one that's currently drawn? We start at the top, and one complete wave is from here, then all the way back to where we started, which was at the top. Looks like that happens after 4 meters. So we want the same amplitude, so we're going to draw our new wave that we'll draw is going to have the same amplitude of 0.1 meters. But we want half the wavelength, so that's supposed to mean m. So for half the wavelength, instead of 4 meters, we're going to have a wavelength of 2 meters. Alright, so I'm going to start at the top, and again, we have to complete that whole cycle at the 2 meter mark. So I like drawing a few points to help guide me along. Alright, halfway through we should be at the bottom, right? So I need to hit this point right here, and I'm just going to kind of fill in the rest. There we go. And that's a good answer. That would work for, that would work. Here's something else you could have done. For a lot of students, particularly as you're first learning it, starting at the top is it just looks different. It's a little bit weirder. If you didn't like that, here's something else you could have done. No. You could have just started at the bottom. You can just start at the bottom, and as long as you have an amplitude of 0.1 and a wavelength of 2. That would be fine. So again, we just need that amplitude of 0.1 and that wavelength of 2. So I'll start at the bottom. Again, we have to go all the way up, all the way down, then back to where we started at the 2 meter mark. We're going to try and make it symmetrically here. So let's try crossing the axis here, meaning let's go up, down, back to where we started. And this would also be a perfectly fine response because it checks all of these boxes here. It's got an amplitude of 0.1, meaning it goes up to 0.1 and down to negative 0.1. And has a wavelength of 2 because it finishes the whole thing in 2 meters. So this looks good. One more time for number 4. Try this on your own. I'm going to give you a second to pause it and give this a shot. Which I hope you did. The transverse wave is illustrated on the grid to the right. What is the amplitude of this wave? So the amplitude, remember, it's how high up it goes and how far down it sinks. It's from how high the crest is, how low the trough is. So the amplitude, reading this, I'm hoping you just went with 0.2 meters. I hate that. 0.2. And that's it. Again, I'm just getting that from this. That's how high it goes. That's how low it goes. That's the amplitude. What is the wavelength? So again, I just trace with my finger. I start here. I go all the way up, all the way down, back to where you started. Looks like that happens in 3 meters. Cool. That's it. Just kind of reading it. Okay, give these last 2 a chance again. You can pause the video, give both of these a shot, and then I'll go over them. Alright, 15, 3 waves, A, B, and C, travel 12 meters in 2 seconds in the same medium as shown. What is the amplitude and wavelength of A? So I'm doing the amplitude and wavelength, amplitude, wavelength, amplitude, wavelength. Alright, it's a busy diagram, there's a lot happening, so I'm going to draw over these to highlight them. Wave A goes from here to here to here. Right, that's wave A. So let's do the amplitude first. The amplitude is... Okay, this one's a little bit tricky. And I do like this question. This whole thing is 4 meters, right? But we don't measure the amplitude from the top all the way to the bottom of the wave. We don't do that. We measure it from that equilibrium point, or that middle point. So if this whole thing is 4 meters, then what is this value? I think that it should be 2 meters, right? Again, if this whole thing is 4, but that's not how we measure amplitude. We go from here to the top. So the amplitude is 2 meters. Onto the wavelength. For the wavelength, okay, it looks like this whole thing is 12 meters, right? But the wavelength is, by definition, the length of one wave. So let's figure how many waves we got. So I'm just going to follow this through. I got, oops, 1, 2, 3, 4. It looks like we have 4 waves in the 12 meters. How could we figure out each individual one? Well, I would say we do 12 meters and just divide it by 4. That gives you a wavelength of 3 meters. If you're trying to figure out how that makes sense, let's just do this. I'm going to sort of count along as I go. Remember, each wavelength would be 3 meters, so that's 3, 6, 9, 12. That fits perfectly with this 12 meters. So it makes sense that each wave would have a length of 3 meters. The next through I'm going to move through a little quicker because, kind of the same thing over again. What's the amplitude of wave B? So wave B, just to highlight it and make it a little more clear where it is, it's this guy right here. Alright, amplitude, remember, is from that middle line to the top of the line. I think that that's 2 meters. Okay, so it looks like wave A and wave B have the same amplitude. Wavelength, though, should be different here, because B looks like a lot more stretched out. Let's just trace out one complete wave here. From the start, we go all the way up, all the way down, back to where you started. It looks like this is only one wave. So it has a length of 12 meters. Remember, lambda is wavelength. I'm calling it 12 meters. Alright, wave C. Amplitude and wavelength. So, again, I'm just going to trace it out to make it a little easier to spot. Okay, that's wave C. And I only traced out one complete wave because it'll help us figure out how long one wave is. Alright, let's start with the amplitude. It definitely looks shorter than A, right? Because it doesn't go quite as high, it doesn't go quite as low. Again, amplitude is just from that middle to the top. I'm going to call that 1 meter. For the wavelength, alright, we've got 1 wave, 2 waves. So we got 2 waves in 12 meters. I think each individual should be 6. And I got that by doing just 12 divided by 2. There we go. Alright, 16, a nice regions question. Based on the wave shown, determine the wavelength and amplitude of the wave. Let's start with amplitude, because I just think that's a little bit simpler. Remember, amplitude, I gave you this whole 1.2, but a lot like the question we just looked at, I don't think that 1.2 is the amplitude. Because we don't measure wavelength from crest to trough. We measure it from that middle to the top. Alright, from the middle to the top. Well, if this whole thing is 1.2, then I think from the middle to the top should be half that. Half of 1.2. Alright, 1.2 divided by 2 is 0.6 meters. Cool. Alright, now, we gotta find the wavelength. So we've got a full 8 meters here, right, from here to here. But that's not a wavelength. The wavelength is 1 wave, meaning like, I'm gonna trace 1 wavelength out. From here, all the way to the top, to the bottom, and back to where you started. That looks like 1 complete wave. Okay, let's figure out how many waves we're looking at, because then we can figure out how long each individual one is. Take a second, pause this, and you know, trace this out, figure out how many waves there are, and I'll wait. How many waves did you get? Was it 2.5? I hope. Tracing this out. All the way up, down and back, 1. Up, down and back, 2. Up. Okay, I'm going to call this leftover part a half. Because you see how it's like the upwards part of the wave, but not the downwards part as well? That's only half of that motion. It's the up and not the down. So I would call this 2.5 waves. Alright, we've got 8 meters, 2.5 waves. How do we figure out how long each part is? I think we should divide, just like we did up here. Right, we took that total length divided by how many waves there are. It's a little easier to think about when the number's easy, like 12, 2, and 6. But we can take the same logic and apply it here. We've got 8 meters. We're going to divide it by 2.5 waves, which is 2.5. And you get, I think I got 3.2 meters there. 3.2 is what that says. Cool. So that's amplitude and wavelength. The last thing we need to talk about here is something called phase, and this is one of the weirder ideas that we talk about. What phase is it's used to represent the point on a wave. So it represents how far apart 2 points on a wave are. This should say 2. So, a little bit of sort of like terminology and how you would use this. When 2 points, we represent phase. It's measured in degrees, which is a little weird. If you're in pre-calc or maybe trig, again, I don't know which class they do this in, they might do it in radians, like 2 pi radians is the full cycle. We're going to use degrees for this class, for regions physics, so we don't have to dive into radians, which is nice. For phase, so, the way we kind of use this term is if 2 points are what we call in phase, we're not writing, they are at the same part of the wave. And we consider one full wave to be, that's an arrow. 360 degrees. So a full wave is 360 degrees. That should be easy to remember because it's like a full circle. A full circle is 360 degrees around. A full cycle is 360 degrees for these waves. Now, if they're not at the same part of the wave, so when I say in phase, like I'm going to use this diagram down here to illustrate. This is a point on a wave, this little x. If I drew a point that was, again, we use the term in phase with it, is the physics term that we use, it means it's at the same point of the wave. Meaning, if this is at the top of a wave, this would be at the next wave. We call those 360 degrees apart. One complete wavelength. That's in phase with one another. Delete that. But obviously not all parts of the wave are in phase with each other. You could have, let's say, out of phase. Actually, and I'm going to be more specific. I'm sorry if you wrote that down. Let's do this by degree. So let's say you're 180 degrees out of phase. If you're 180 degrees out of phase, you are on the opposite part of the wave. Which would be a half a wavelength. So I'm going to just write in 1/2 lambda. Alright. Turn that down. Okay, so you are an opposite part of the wave. So if you're 180 degrees out of phase, you're on the opposite part of the wave. As an example, let's say you're at the top here. Well, right, that's the crest of the wave. Let's say you're not 360 like a full wave. Let's say you're only 180 degrees out of phase. Well, if this is the full wavelength, then 180 degrees would be a half that, which would be like right here. That would be this part of the wave. Can you see what I mean by the opposite part of the wave? So if we start on the crest, the opposite part would be the trough, that bottom part of it. So that's 180 degrees out of phase. We could keep going. I'm not going to write it all down, but if you were 90 degrees out of phase, so let's say we have this top part. 90 degrees out of phase. All right, well, let's keep that going here. If the full wave is 360 and then half of it is 180 degrees, then 90 degrees would be like another half of that. So it's a quarter of the wave, and so on. So if you're trying to like remember this in one quick fact, I would simplify it to this. Phase is where you are on the wave, and a full wave is 360 degrees. And then the rest of the degrees you could work out from there. So like 180 is half of that, 90 would be a quarter of that, and so on. It's a weird idea, but I think just a couple examples and you'll really get the hang of this. Try questions 17, 18, and 19 on your own. So do these all on your own. 17, 18 I think you'll be able to get through. 19 is a little tougher, but try all of these on your own. I'll give you a second to pause the video and give them a shot. Alright, I'm hoping you took that time to pause the video and try all of these. Let's go. 17, 18 are multiple choice questions that I just took the multiple choices out of. The diagram to the right shows it's supposed to say periodic wave. Which 2 points are in phase with each other? Alright, in phase means they're the same part of the wave, separated by one complete wavelength. What I would do is I would just start with A and like work from there. So like A is like here. Again, a full wave is like all the way down, all the way back up, all the way back to where you started. So if we start here, anything that's in phase should be just as high up as point A. Because, again, in phase means the same part of the wave. So right away, B like is not at the same part of the wave as anything else, so that doesn't work. Alright, one complete wave is all the way down, all the way back up. Now, the answer is not A and C. The reason is this. See how if you're tracing with your finger at point A, you'd be going like downwards, like, you know, traveling like down along this slope? Point C, if you were traveling, you know, again, if you're following with your finger, you're going up that slope, you know, like up this way. that's not the same part of the wave. The medium is moving in a different direction, so it's not A and C. I'm going to follow this until I reach point D, and actually the correct answer to this one is A and D. A and D, because they're at the same height, and you see how at point A, like, you're going downwards, like, towards this equilibrium, like, middle line, and at point D, you're also going downwards towards that equilibrium middle line. So A and D are in phase at the same part of the wave. They are one full wavelength off of one another. 18, which is in phase with point P. So kind of like before, we've got point P right here. If we're in phase, we're at the same part of the wave. It should be just as high up. So A is wrong, D is wrong. The answer is either B or C. But which one? They're both on that middle line. They both seem like good guesses. I'm going to follow one complete wave, because that's what in phase means. All the way up, all the way down, and back to where you started. All the way up, all the way down, back to where you started. The answer to this is point C. B is actually 180 degrees out of phase. It's on the opposite part of the wave. Because you see how like point P is on that equilibrium line going up? And then point B is on the equilibrium line going down. That's a different part of the wave, so that wouldn't work. The answer to this one is C. Last up. The diagram below represents a transverse wave traveling through a rope with point A labeled as shown. We're drawing a point that's 180 degrees out of phase and labeling it B. And then we're going to do something that's in phase and label that point C. I'm actually going to do this part first, because in phase is just always easier. You have to draw the same part of the wave wherever it was. A is at kind of a weird point. So again, we have to go all the way up, all the way up, all the way down, and back to where you started. This is where we should be drawing that. We're calling it point C. So that's point C. That is in phase with point A. The easy mistake to make would be to draw it here, and that wouldn't be correct. I think point A, like it's not perfectly at the top or at the bottom. It's kind of like an easy point to analyze. So what I like to do is I like to do this. I like to pick an easy point that's nearby. Meaning, if I drew point A here, this would be an easy question because point C would be here. But point A isn't all the way at the top of the wave. So what I'm going to do is I'm going to move both of them like backwards a little bit. So I'm going to move point A down to here. But remember, A and C have to be lined up with one another. So we're going to move point C down to there. See how again, the tops are definitely like the same distance apart. I just kind of moved them both over a little bit. So that's actually the answer to part B. So for part A, on the diagram, draw a point that's 180 degrees out of phase. So 180 degrees, remember, is a half a wavelength. It should be the opposite part of the wave. Two ways to do this. I'm going to use that thing that I just told you to do, which is pick easy points and work from there. Meaning, let's change colors. If it was all the way at the top, this would be easy. The opposite part of the opposite of the top is the bottom. The opposite of the crest is the trough. But A is like a little to the left of that, so B should be a little to the left of that. And this would be your point B. If A is above the line, B should be below the line by about the same, or by exactly the same amount, if it's 180 degrees out of phase. Another way to do it is if you know the full wavelength, 180 degrees would be like cut that in half, which I think would be like roughly here-ish. So that would be a half a wavelength, or 180 degrees. So that's phase. It's the point on the wave, like how this compares to that. A full wave is 360 degrees, and the rest you can kind of work out from there. And that's it. That's it for this. You have a quest to go with this, I think. If you get stuck on that, please email me.